This video will talk about a special kind of factoring that's called a difference of squares. So a difference of squares happens when you have a set of binomials such as this, where the terms are exactly the same, only one sign is positive and one sign is negative. Let's see what happens if we were to FOIL these together. So in this case, x times x would give me x squared. X times negative 3 would give me minus 3x. Positive 3 times x would give me plus 3x. Positive 3 times a negative 3 would give me minus 9. So then on this next step, when I would be ready to combine my two x's in the middle, you'll see that they actually cancel out. Negative 3x plus 3x gives you 0 x's. So all you're left with is just x squared minus 9. So now let's look at what characteristics make up a difference of squares. So you can see here that it usually has only two terms, and that both of those terms would have to be what's called a perfect square. So perfect squares are numbers such as 1, 4, 9, 16, 25, etc. And the way I'm coming up with these numbers is 1 times 1 would give me 1, so 1's a perfect square. 2 times 2 would give me 4, so 2's a perfect square. 3 times 3 would give me 9, so 9's a perfect square, and so on and so forth. It's also important to realize that x squared is also a perfect squared because x squared is created from x times x. And similarly, x to the fourth is a perfect square because x to the fourth comes from x squared times x squared. So your two terms must both be perfect squares, and most importantly, you must have a minus sign in between those two terms. So let's look at our first example. So I notice there's only two terms in this polynomial, so it indicates to me it could be a difference of squares. So when I investigate studying both of these terms here, I see x squared is a perfect square, 25 is a perfect square, and I have a minus sign in the middle. It's a difference of squares. So the way I would factor this is set up my pair of binomials here, and then what would the square root of x squared be? Would be x and x. Then what's the square root of 25? 5 and 5. And from there I know I should need 1 plus and 1 minus. And again, you could FOIL that back together to see that you'd end up with x squared minus 25. It's important to keep in mind that you always must have a minus sign for this formula to work. So if you look in part B, although both x squared and 25 are perfect squares, I have a plus sign in between here. There's nothing we can do to factor this polynomial. It's called prime, meaning I can't factor it. So coming down here to question C, again, this is where you want to pay attention to the hint that you should always start your factoring problems by looking for GCF. So when I look at this one, I notice that I have a GCF of 2 that will divide into both of these terms. So as we did before, remember we write the GCF outside of the parentheses like this, and then divide the GCF out of each term, and what's left over after I divide is what goes inside the parentheses. So 2x squared divided by 2 gives me just x squared, and 32 divided by 2 gives me minus 16. Okay, remember that your GCF must follow you all the way down to your final answer. So when I look inside of these parentheses, now I have a difference of squares. Both x squared and 16 are perfect squares, and I have a minus sign in the middle. So to get my two factors, then I just square root each of these terms. X square root of x squared is x and x. Square root of 16 is 4 and 4. And I know I'm going to need 1 plus sign and 1 minus sign. And here's my answer completely factored. Looking up here at problem D, it's a little bit misleading because it kind of looks like a difference of squares. I know x squared is a perfect square and 100 is a perfect square, but my signs are off. So remember that before you start factoring, you always want to make sure that your x squared term is positive. So for this one, we're going to treat our GCF as negative 1. So put your GCF outside the parentheses like this, and divide negative 1 out of each of these terms. So negative x squared divided by negative 1 gives me a positive x squared, and positive 100 divided by negative 1 gives me minus 100. And you can see that by doing this, it's fixed my sign problem. Now I have a difference of squares inside the parentheses. Okay, remember that your GCF must follow you to the answer. However, it's not necessary to write the 1. You can just leave the negative outside the parentheses like that. So now if I square root x squared, I get x. And if I square root 100, I'll get 10. And I know I need 1 plus and 1 minus. And there's my final answer, completely factored. Okay, looking here at problem E, this one again may be a little confusing because it doesn't look like a difference of squares at all. But when I take a closer look, I see that I have a GCF of 9x that will divide out of both of those terms. So bring your GCF outside the parentheses. Divide 9x into each of these terms. 9x cubed divided by 9x gives me 9x, it will give me x squared. And negative 9x divided by 9x gives me minus 1. So your GCF must follow you to your final answer. And then when I look inside x squared minus 1, I have a difference of squares. So split up your binomials. The square root of x squared is x, so I get x and x. Square root of 1 is 1, so I have 1 and 1. And I should have 1 plus and 1 minus. And there's my final answer, completely factored. The last one here, problem F. I may be in the habit of looking for GCFs, but when I look at this one, there's not a GCF that divides into both 9 and 25. However, at a closer look, both 9 and 25 are perfect squares, and I have a minus sign in between. So this is already a difference of squares without having to divide out a GCF. The only difference is the 9 being in your first term. So again, I just think to myself, what would the square root of 9x squared be? It would be 3x. So my first term will be 3x. And then the square root of 25 would be 5 and 5, and I should have 1 plus and 1 minus. And again, if you were to factor that, boil that back together, you would see you got the same polynomial we started with.